welcome everyone to our 15th CUDA mode lecture here on the CUDA mode Discord server, our highlight event of the week. I'm super happy to have Eric Ault today here, who is going to talk about CUTLASS. Something which I have not looked deeply into, and I'm super excited to learn more about, and it's also something I want to personally spend some time really with this library in the future. So this is really great to have him. In general, these sessions that we do go for about 1 hour, like plus minus whatever is required, and also we have a Q&A session normally at the end. So if you have questions, please, the simplest is you ask them in the chat, and we'll try to somehow pass them on, forward them to Eric during the talk. I'm really excited. Please go ahead.
Great. Okay, let's get started. Okay, so first of all, let me shout out some of the authors of this library. These are some great people at NVIDIA. I'm sure there's even more that I didn't encounter in my travels, but these are just some of the people that are responsible for this library, and I thought they should be thanked. Okay, so what's the point? Like, why would you even want to learn this library? Well, you might not, but if you do, I think that some of the things that are rewarding about it are it's actually kind of pretty. And I'm coming from a math background, and I think that it's interesting about this library that a lot of it almost has a universal quality to it that you would think any library that adopted this task would need to have this structure in some ways. So I think that's kind of pretty from like a mathematical perspective. And that is sort of what I wanted to focus on in this talk a little bit. So there's a lot of directions that I could go in this. The library has a lot of kind of nuts and bolts, and there's a lot of, there's kind of a big API for it, a lot of moving parts. There's kind of layers to it. So as you'll see, there was kind of the original CUTLASS, and then when CUTLASS 3.0 came out, there was kind of this extra layer added to it. But the part that I wanted to focus on, and where I think I might be able to add the most value, is to think about the conceptual part of it. And hopefully I can sort of, loosen the lid a little bit for people that want to come in and learn it. And I'm sure all you guys are, real good coders and better coders than I am, so you can learn the API and everything yourself. So I'm not going to focus as much on learning all of the ways into the library, but I want to sort of get the conceptual part emphasized. Okay. And as another piece of motivation, if you go to, for instance, the Flash Attention repo, and once you actually get down to where the code is running, you will immediately encounter CUTLASS. So, if we are looking up to Flash Attention as one of the kind of key examples that motivates our focus on performance in this group, then CUTLASS is definitely going to take a large role in learning how to write performant kernels and stuff. Okay, so how do you even know if you are looking at a CUTLASS piece of code? So there are these kind of telltale signs. One of them is these underscores. So CUTLASS has this indexing convention where if you have a tensor called some tensor, you'll have then parentheses. So you actually index with round parentheses, not the square brackets. And then the indices come separated by commas as usual, but the underscore is like the colon in Python. So it's like the slice, give me everything in this along this dimension, but only the second coordinate in the first index and stuff like that. And then there are these kind of the greatest hits functions that show up over and over. There's got local tile, local partition, partition D, partition S. This is an interesting one, _3. So that's CUTLASS's way of representing a static 3. So it's a 3 where the information is embodied not in the value of the variable, but in the actual type. So if that's clear to you, then great. And if not, hopefully it'll become more clear as we go on. All right. So in what situation would you want to adopt CUTLASS? Well, if you're writing a pretty straightforward linear algebra computation that people have done thousands of times before, you probably don't want to reach for CUTLASS. You probably want to reach for something like CUTLASS. So it's worth kind of dividing the libraries that come from NVIDIA into two parts. The first part, the kind of, you might think of it as the somewhat more user-friendly part, are the ones that you just call from the host, right? So you don't have to write any kernel code yourself. These are things like CUTLASS, cuDNN, and stuff, and they're very customizable. You can do a lot of things with them, and you just call them straight from the host. So these libraries will infer whether and when to use like tensor cores, for example. So they do a lot of the work for you, and they're very good for like kind of very straightforward applications, is my understanding. I've not used them a lot, but of course, when you do invoke such a function, you are making a trip from and to the device, right? So that's just, you have to know that you're doing that. Some of these libraries, like I know CUTLASS, for example, does have the ability to do some kernel fusion, so that you don't always, strictly speaking, have to, if you invoke a function, if you invoke the composition of several functions, you don't have to come back and forth to the host each time. So they can fuse some kernels together for you, but generally speaking, you have a limited amount of flexibility there. And then, of course, there are these libraries that you call from the device, and that's what we're talking about today. Other ones besides CUTLASS are, excuse me, so you've got Thrust, you've got Cub. So CUTLASS is one of these. It has low-level control. The tensor core operations are exposed directly, so you're going to see that. And so the time when you would reach for it is like if you want to take a new ML model that has just come out and sort of spec it out and like test whether and how it can be made performant. So if you are a person who is exploring this space of like kind of performance-oriented machine learning models that incorporate a lot of linear algebra, as most of them do, this can be a good tool for you because, if it's a newer model, CUTLASS might not have the requisite flexibility to incorporate it. And so this is a good place to start or to get expertise in for people that want to play that role on a machine learning team of like, okay, I'm the person that's going to go make this kernel. I'm going to, come back and say like, the reason why this is not fast yet is this, and if we wanted to change it, we would have to do this. All right, so this is going to let you get your hands on the levers like very directly. So just a little notation clarification, first of all. I'm using this kind of like Donald Knuth notation where it's like the square bracket on the left, and then two integers separated by these two periods. So that's like a half open interval of integers. And then there's this term called mode that comes up a lot in Qt. In CUTLASS. Qt is CUTLASS 3.0. That's just a term for CUTLASS 3.0. It's Qt, the CUTLASS tensor, or I should say CUTLASS tensor notation. So that's what Qt means. And this thing that's called a mode, that's the notion of like we have these nested tuples that we're going to be talking about, and they're tuples of integers. And so each element of a nested tuple, which is possibly a tuple itself, is going to be called a mode. So it's easy for me to kind of move on and forget that that's terminology that I was confused by at first. But just to kind of clarify right up front. Okay, this is just like a very broad overview of what we're going to be looking at. And I hope to return to this picture again so that you don't have to just like store it in your memory this entire time. But we're talking about like tensors. And before I describe what these things are, I just wanted to give you like the bird's eye view. A tensor has like an engine, and that's something like a pointer, basically. So like the underlying memory. And then it has a layout, and the layout is a shape and a stride. And each of the shape and the stride are these like nested integer tuples. Okay, let me just pause for a second. Is everything going well? Are there any problems at this point? Any questions? I'll just take a breath here.
I think it's all good right now.
Okay, great.
So
We'll
if
move on
somebody
and
has
start to.
questions, if somebody has questions, please ask in the chat.
Okay, but I'm glad to know that everyone's receiving this, and we'll move on and put some meat on this now. Okay, so I want to start building up some of these concepts by just thinking about normal C-style indexing. So if you work with tensors a lot, as you probably do if you're in this group, you see a lot of times that like you start with a coordinate ij, and then in order to get the linear offset of that coordinate, you do something like I plus j times m. Or if it's three coordinates ijk, it's something like I plus jm plus kmn. And those, the red m and n could come after the I, for instance, depending on how the memory is set up. So it's not necessarily that the m goes with the j and the mn goes with the k, but this is like the kind of familiar structure of taking a logically tensor coordinate and mapping it to some linear offset of memory. And that's like a very fundamental thing about CUTLASS, is like that a lot of the abstractions are meant to do things like this in a way that is less prone to mistakes and less brittle. Okay. So what I want to do is think of this as a dot product between two little vectors, so that the I plus jm plus kmn is actually a dot product of the green thing with the red thing. And that's like our starting place for building up these concepts. All right, so the thing in red, we'll call that the stride, just to start with. Oops, what happened here? Yes. Okay, so if we are using this m and mn like this, usually it's because the allowable coordinates are like 0 to m in the I direction, 0 to n in the j direction, and 0 to k for some k that has not shown up in the problem yet. And we're going to encode the allowable input coordinates as a thing called the shape. So that's what we saw before. Just to back up to where our picture a moment ago, we had, so these tensors are composed of an engine, which is like the pointer, and then the layout, which is the shape and the stride. So both of the shape and the stride are these like nested integer tuples, and we're going to have the shape represent the allowable input coordinates, and the stride is that red thing. So the stride is how you go from a coordinate to an offset, to like a memory offset, which allows you to get the information that you want to access. Okay, so the way we're going to write these shapes, which, as I was saying, specify the allowable coordinates, is just to specify their upper bounds. So we're going to have like tuple capital M and K. So that's the shape. So it's understood that each coordinate, starts at 0, so that the shape capital M and K means that, okay, I'm allowing coordinates between 0 and M in the I direction, 0 and N in the J direction, and 0 and K in the K direction. All right. So we're going to call this assembly of a shape and a stride a layout, and separate them by a colon. So this is the one we were just looking at. The shape is MNK. Remember, that's the allowable inputs. Okay. And then the stride is how to get from a coordinate to an offset, right? So I take whatever the input coordinate is, and I dot it with the stride in order to get the linear offset. Okay, so often I will mix up the terms shape and size. Those are definitely not the same thing, but you can see why I do, because the shape delineates which coordinates are allowable, so it is something like the size. Okay. So another thing we can do is like take this like concatenation of layouts. So if I have a one-dimensional layout that's like 3:1, I could concatenate that with 2:3, and then that's just the same as saying 3:2:1,3. So this is not, I'm not like claiming anything about layouts here. This is just a notation. And sometimes it's more convenient. So you can feel like the red 1 goes with the red 3. The 1 is the stride, and the 3 is the shape. it can be more convenient sometimes to have the stride closer to the shape that corresponds to it, as opposed to giving like the entire shape and then like going back and giving the entire stride. So this is just a notation that allows you to do that in a more compressed way. Okay, looking good so far. Okay, so this is a little bit trippy at first. You can have nested layouts, so that you can have these like inner. So this layout that we're looking at right now, which is the tuple 3, 4, and then comma 2, and the stride tuple 1, 3, 40. Okay, so what's the difference between this and the sort of flat version, which is like 3, 4, 2, colon 1, 3, 40? Just the difference is just the kind of coordinates that it accepts. So this one that is not flat accepts coordinates where the first coordinate is itself a tuple, right? So in here we're looking at the coordinate 1, 2, 1, and it has two modes. The first mode is 1, 2, and the second mode is just 1, right? So it has this kind of like tree structure. But the flat one accepts coordinates like 1, 2, 1 with no nesting, right? So there's this notion of like congruent in Qt/CUTLASS, and it just means that they have the same nesting structure. So the shape and the stride always of a layout have the same nesting structure. And also the coordinates that they accept have that same nesting structure. So you can see above, like the not flat layout, the 3, 4, 2 with the nesting, accepts the coordinate 1, 2, 1 with the same nesting, and then the flat one accepts flat coordinates. So I hope this is clear. I can clarify if it's not. But just the notion is that like the shape, the stride, and the coordinates that it accepts all have to have the same nesting structure to make sense. Okay, now I'd like to talk about drawing layouts, which I think can be a kind of a weird thing at first. To me, it kind of. So let's just kind of go down the line here. So let's take a simple one. And this way of drawing things is it's not to provide like a rigorous definition of what the layout is, but it can help you imagine what they are and to help you kind of reason about like what they should be. So let's take like a very simple one. So like 3, colon 1, 3. Is that coming through okay? Can everyone see?
Yes, it's very, very visible.
Great. Okay. So let's start from the left and work our way to the right. And we'll see later that we can actually start from the right too. It doesn't really matter. So I'm just going to label these coordinates here. So the first one I'm going to call, let's say I, and this one I'll call J. So first of all, I'm going to specify as I draw it, like which direction is the positive I direction. And we'll just kind of use this, like the one that is typical for matrices, where you draw the positive I direction going down and the positive J direction going to the right. And again, this is just a way of imagining things. It doesn't really represent anything. The point of the whole Qt framework is that it's an abstraction over the actual layout of the memory. But so what we're going to do is first we're going to look at, okay, what is the size in the I direction? It's 3. Or I should say the shape in the I direction is 3. See, I confuse size and shape. And what is the stride? It is 1. Okay, so the way we're going to draw that is to say, always starting from 0, we're going to have 3 entries, and they're going to be strided by 1. In other words, they're going to have a space of 1 between them. So that's pretty simple. It's just 0, 1, 2. Okay, and now it's compositional here. So as we look in the J direction, what we're going to do is say, okay, we have 4 elements in the J direction, but every element is everything we've done so far. In other words, it's compositional. So this, now we have to consider everything we did so far as an element. So the thing that I just circled is one element in the J direction, the way I'm writing it. And then we reproduce that element 4 times. And because the size is 4, and the stride is 3. So I reproduce that element 4 times. Well, I've already done it once, right? So here's the first one. There's going to be 4 of them, 1, 2, 3, 4, and they're going to be strided by 3, which means that each element is offset by 3. So the 0 becomes a 3, the 1 becomes a 4, and the 2 becomes a 5. Okay, and then I do it again. That's the second element, the one that I just drew in the j direction. So maybe this is too clear and I'm belaboring the point, but this is just a way of thinking about it. So 6, 7, 8, and 9, 10, 11. Okay. So let's think about it now reversed. Let's think about 4, 3, colon 3, 1. Okay. So in a sense, this should be like the same layout, except with the I and J's reversed here. So first I'm going to draw the positive I direction. Again, this is going to be I, that's J. Okay. I'll draw the positive J direction. Okay. So I'm going to have 4 elements in the I direction. So I'll draw them here. 1, 2, 3, 4. I always start from 0, but they're going to have stride 3. Right. So what I'm going to do is start from 0. That's one element. Excuse me. So 0 is the first element, and then I have to stride by 3. So 0, 3, 6, 9. And then in the j direction, what I see is I have 3 elements. And I remember that the thing that I just drew, I'm going to consider one element in the j direction. So I want 2 more of those for a total of 3. And they are strided by 1. So that means that as I move to the right, every element increases by 1. So as expected, this is just going to turn out to be, excuse me, that was wrong. This is going to turn out to be the same thing but transposed that we just did. Okay, but the point is that once we start to get a little bit more complicated with these layouts, you can hopefully extend your ability to reason about them. So you see how this one is just the transpose of the thing we did before, and it resulted from just changing the I and the J modes in both the shape and the stride. All right, so let's think about a higher dimensional one. Let's think about 2, 2, 4, comma 1, 2, 4. All right, I'm going to move this down a little bit. So let's draw I, J, K. Here's I. Here's J. And then I'm going to have to draw the K direction sort of going into the page. And we'll do that in a second. So first I have 2 elements in the I direction, right? Because the shape in the I direction is 2, and they're strided by 1. So I'm going to get 0, oops, 1, 0, 1. Okay, now everything I've just done becomes an element, and I'm going to go 2 elements in the j direction. So I've already done one of them in the j direction. I do one more, strided by 2. So the 0 becomes a 2, the 1 becomes a 3. And now I have to draw in the k direction. So I'm basically going to have like 4 pages, you could think of it. So here's the first element in the k direction. It's everything I've done so far. Axis back. Okay, so I'm going to circle the elements in the k direction. So here's the first one. Okay, and then they're all strided by 4. So I'm going to have to increment them all by 4. So 0, 1, 2, 3 becomes 4, 5, 6, 7. That's the second element in the k direction. Then I get, as you would expect, 8, 9, 10, 11. And then my fourth element in the k direction is what you would expect. It's 12, 13, 14, 15. Okay, so maybe this is getting tedious, and if so, that means that it's good because you understand it. So there are a couple of like special strides that you can specify, and I'll talk about those now briefly. So given a shape, so suppose I have a shape like A, B, C, D, like that. I can sort of do a really automatic stride. So I can say something that's called layout left. Okay. And what is that? Well, it's the stride that is the running prefix product going from the left. So the layout left stride is, in this case, 1, A, AB, ABC. Okay. Okay, and what does that mean? So it means that, well, if I have a coordinate, and let's say I have like a coordinate, I don't know, 3, 2, 0, 5. Say that's my coordinate. And if I'm using this as the stride, then the offset that I get is 3 times 1 plus 2 times A plus 0 times AB plus 5 times ABC. Okay, and this is sort of, you can think of this as like a generalized row major. So you'll often see in the code, like, you know, you just want to specify the shape, and then the stride kind of comes for free. So you don't have to use layout left, but you can. Another one is layout right. So that means that you take the running product coming from the right instead of the left. So let's look at A, B, C, D with layout right. Okay. And it becomes A, B, C, D. And now I'm going to take the prefix product coming from the right, exclusive. So 1, B, C, D, and then B, C, D. Okay, is that clear? Let me pause for a moment and just see if people understand what I'm talking about so far, and if anybody has any questions. If this is boring, then that means that it's clear at least, and if it's totally muddy, then that's bad.
Yeah, I think there's a question from Jonas who says, wait, shouldn't it be generalized column major in the first index if the first index is continuous?
Oh, did I say row? Yeah, that's true. It is column. Thank you for clarifying that. Yeah. So this one is column. Yeah, the right layout right is like the generalized row. Thanks for catching that.
Also, really nice that you like draw everything, like write it up live, and yeah, makes it.
Good. I hope it's clear enough. Okay. So feel free to interrupt with questions, but let's just keep going a little bit and then talk about how we can think about this more. So what about, like, if I'm going to try to think about a subtile now. So let's imagine, I don't know if I want to do 2 dimensions or 3 yet, but let's imagine that I have this tensor here, and I'm kind of zeroing in on a little subtile of it. So let's say that this tensor is like, I don't know, MN is the shape, and then let's say it has like layout left. So that would be 1M as the stride. So just to refresh, that means that if I have IJ as the coordinate, then I get offset I plus JM. Okay. Now, what if I just want to zero in on like a little tile of it with coordinate m, and actually I'm going to make this concrete. So let's say that this tile size is, let's say it's like 3 and 5, and let's say that this is the second, let's say it's the third tile down in this direction, and let's say it is the I don't know, like the second tile to going to the right. That literally doesn't look right, but whatever. Okay, so then this point here is one to the right, so that is the point 5, comma 6. So that's the upper left corner of this box, right? So how would I express a subtile of another larger tensor? Let's think about that. So, well, if I were going to say that this thing here is its own tensor, well, first of all, it's going to have a different offset than the original tensor. So this, let's call this big thing capital T, and let's call this little thing little t. Okay, so we saw that this is the layout of T. So that's, as I said before, the layout of T is that. Now, what is the layout of little t? That's what I want to get to. So, well, by definition, I've told you that the shape of little t is 3, comma 5, right? So it's like this smaller version of capital T. But what is its stride? That is a question that I want to focus on. So in order to answer that question, I mean, I could sort of poll the audience if I were live, and I would see if anybody thought about it. But you know, in lieu of that, since we're on electronic here, let me just ask the question: if I increment 1 in the I direction, how much does the offset change? Well, it changes at the same amount that it did before in the larger tensor. So the stride in the I direction is still 1. Okay. But then what if I increment it in the j direction? So what if I go from here to here, keeping the I direction constant? Well, the amount that it changes is still the same as it was before. So the upshot of what I'm trying to say here is that when you take a subtile, the shape changes, but not the stride. Okay. So also, though, we have to point out that every tile here would have the same shape and stride. So they're not the same tensors, obviously, right? So this tile would have the same shape and stride, so would this tile here. So what's different about them? Well, what's different is their starting offset. So if we go back, we saw this picture that said like a tensor as what's called an engine, which is basically like a pointer. You can think of it, the base pointer. Oops. Back. And then it has a layout. And that layout is itself composed of a shape and a stride. So the point is that the different tiles, the different subtiles, so we could call this little t1, and then there's like maybe this is little t2 or something. They would all have the same layout, but their base pointers would be offset by a different amount. So the base pointer of this one that I drew here, because it starts at index, let's calculate it. So it starts at index 5, comma 6, which we can use the original layout to take that to what offset that corresponds to. So that's 5 times, well, let's look back up at the stride. It was 1, comma m. So then in order to get to a coordinate to an offset, we do the dot product, 5 times 1 plus 6 times m. So that would be the starting offset of this subtile here. So the point, just to sum up what I just said, a subtile has the same stride but a different shape and a different base pointer, because, you know, like in C pointer arithmetic, we would say that the base pointer of t sub 1 is offset from the original pointer by this amount. Okay, let me just pause there for a second, and people can tell me if I'm going too slow, too fast. Take a drink of water here. Anybody have any questions?
I think that's like a really nice introduction about the tensor strides and shapes that you give this. Yeah.
Oh.
Also, like how you build up that you like explain how this like the offset basically is the most important thing if you just have a subtile. So my question would be, of course, like is CUTLASS like takes it like this at overhead to check every access? Is it like desirable to check it, or is it like at C pointer arithmetics where you just can access also things outside of the if they like specify coordinates which would exceed like go outside the tile.
Oh, yeah. So if I understand your question, you're saying, will CUTLASS allow you to make an illegal
Right.
access
Yeah.
to
Yeah.
like go
Exactly.
out of bounds of a tile? Um, I'm not sure I have a great answer to that. I think the answer is no, that it does do bounds checking.
Mm-hmm.
Um, and furthermore, the fact that I think I remember I mentioned before, you have this like _3 as these like static integers. So part of the sort of complexity of CUTLASS that I'm suppressing here is that a lot of things can be checked at compile time, so that you can actually do a fair amount of the bounds checking at compile time, which is, you know, if you like C++ metaprogramming, that's good because you get hopefully informative errors. Obviously, not everything can be static. You know, you have some dynamic parts of your thing, but you know, you should be able to check a fair amount of like, okay, this layout matches this layout because it's all encoded in their type. So if that's a little bit confusing, I understand because I haven't really explained that yet. But the part of the point of this library is it involves a lot of C++ metaprogramming, also known as compile time programming.
So we have two more questions. One is from
Sure.
ASK or Mask Proga. He asks, are you going to explain on an example what nestedness means?
Oh,
Could you?
yeah. Thanks for asking that because it wasn't something it occurred to me too that it was confusing. So, um, what I mean by I think I understand your question. So you understand what the word nested means. You just want to understand. In fact, this was my very next point. So, what is the logical difference? So, in other words, if I understand your question, 3, 4, comma. Let's look at two different layouts. One, we kind of did this before, like so. 1, 3, 12. So in other words, I think the question is, what is the semantics of this nestedness? So what is, if I have this layout and then I have the flat version, sort of like what's the difference in how they're represented or in the actual memory or whatever like that? I think that might be the question. What do you think, Andreas?
Yes, I think like general. So if you have never heard about nestedness before, basically what it means, what you can do with it. Um, yeah.
Okay, so what it means, just as a matter of terminology, is that the nestedness is that these tuples have this sort of recursive tree-like structure, so that I think of this outer tuple has two modes, which I'm turning modes are like elements, right? And then the first mode is itself a tuple, 3, 4, and the second mode is just an integer 2. So that's what it means for a tuple to be nested. But if you're asking what are the semantics of a nested tuple, in other words, how would these two things, the flat one and the not flat one, differ in the way that they're like represented in memory or in their actual whatever they do in the program? The answer is it depends. So why would we ever want to use a nested one instead of a flat one? It's because of things like this. So, and stop me if I'm misunderstanding the question. So, a lot of times, what we want to use these layouts for, and in particular, the shape. So, suppose we have a shape here, and a shape is just like a tuple. So, this is a shape. We want to say that, okay, it has two elements. The first element is going to represent an arrangement of threads. And those could be maybe one-dimensional or two-dimensional or three-dimensional. So if you've done some CUDA programming, you know that you have this like dim3 object that you pass, and it represents the grid dimension, it represents the block dimension. And so logically, it could be a different number of modes, right? So your threads could be one-dimensional, two-dimensional, or whatever. So if they're more than one-dimensional, it's going to be a nested tuple representing here. And then the second one represents like values. So might not make total sense to you why you would want to do this right now yet, but what we're going to do here is we're going to say, okay, we can change the thread and the value sort of independently. So suppose I have like thread 0. Now thread 0 is going to be responsible for like a range of values. So all the different things I can do here, put here. So let's make it concrete. So suppose I have like a shape that is like 4, 6. And then let's leave the stride aside because the stride really isn't relevant here as far as I can tell. So this is saying I'm going to have like 4 threads in whatever, maybe this is like a tensor core operation or something like that logically has to involve 4 threads. And this one is something I plug in here. It's going to say, okay, for each thread, it's going to be responsible for 6 values. And so then every 2-dimensional coordinate I pass here, like I'm going to say like 2, 3 would refer to like the third value that thread 2 is responsible for. Okay, but the point of the nestedness is that, okay, so either of these could be themselves nested tuples. So I could think of the threads as coming in, 3-dimensional coordinates, and the values themselves as coming in 3-dimensional coordinates. So I could just keep talking, but I hope that answers the question.
So it feels
Andreas, did you say that was?
I'm not sure
Yeah.
if I understood it like correctly. So it feels a little bit for me to have like shapes for me represent like multi-dimensional arrays, so to say. And that now with this like nesting of these shapes, I can basically then like divide those individual dimensions again into like sub multi-dimensional arrays, or how could I imagine this? Like if I have
So that the thing that is about that is that if you look back at what we did before, this was not a nested tuple, right? It was just flat. So we had like 3, 5, 1 n. But I was still able to talk about subarrays, right? So it may be, as Andreas said, that like the nesting, like in, for instance, this one here. So let me draw it. Like the fact that this first mode is itself a tuple could represent, as Andreas is saying, okay, this is a logical place to subdivide the tensor, and maybe this tuple on the left here represents something, and this tuple on the right represents something different. So it doesn't necessarily map onto like, okay, you can only have a subtensor if you have this nesting, right? Because we had this like subtensor up here where it was flat. But it's a logical division, so that like this could be part of, like this one here could be part of an API. In fact, it is part of an API that says like when you pass the arguments to this like complex instruction, like a tensor core operation, the first mode has to be the threads, and those can be a number of different dimensions, or they could just be an integer. The second mode is the values. So yeah, I can imagine this might be getting a little bit complicated. Are there any clarifying questions? Because I feel like talking more might not solve it, but maybe as we move on, it would become more clear.
I think we have another question with it, which is how do you tile a tensor in this example? I think the first example above, the picture you drew, how do you specify this capital T is broken down into like lowercase t's? Like the ST1, for example. Maybe it's like also a semantical question, like, or how is it done effectively in the library later? How you specify like this is like a subview or in this?
Yes, that's a really good question. So if I have a larger tensor T, so like, yeah, so let's talk about how would I create little t from big T in the API. So there's a few different ways to do it. And it runs the risk of kind of overloading you with information here, but so there's important methods. One of them is called width underscore shape. That's a tiling one. There's one that's called local tile. There's one that's called local partition. Oops. And then the one that might blow your mind a little bit is it's just called compose or composition. So I kind of debated whether or not to like put this in the talk, and I'm glad I didn't because it's already going longer than I anticipated, which is great. But so the really fun thing here is that they found a way, and there's this whole section of the docs called layout algebra, and you can actually take two layouts and view them as functions. And so forming a subtile is actually just composing these two functions. So really, this with shape here, if you look at the implementation, all it does is say, take big T and essentially compose it with the layout of little t. So I don't expect that to make perfect sense right now, but those are some places to look for the answer to your question. So please feel free to ask more clarifying questions because that's the way I know what's clear and what's not. So this little circle here is the function composition.
So we have also a follow-up
Should I
question
move
to
on,
this. If this is like adding some hardware overhead, or is it like all it's like at runtime, or is it all at compile time, this composition happening?
Oh, okay. So it could be either. So if the layout is entirely static, so if the layouts that are being composed are composed entirely of like these like _3, the sort of compile time integers that I was talking about, then you can compose it at compile time. But there are some things that would need to wait until runtime. Like for instance, you wouldn't anticipate that the actual dimensions of a big piece of memory that you would pass in would be known at compile time. But on the other hand, the little tile size might be known at compile time. So I might have to wait to do like the big tiling of like a big piece of memory. But some of the intermediate steps I might be able to compute ahead of time, if that sort of answers the question.
Yeah, I think it does. And if like another nasty question, it's like, is it allowed in CUTLASS to use negative strides?
Actually, yes, that's essentially yes. You definitely can use negative
Nice,
strides.
nice.
It's a little bit mind bendy, but and in fact, we haven't even gotten to this yet. But this was sort of my next point. So I'll make sure there are no really burning questions before I sort of elaborate my next point. Yeah, let me know if there's anything that's just totally unclear. But my next point was going to be about non-contiguous stuff. Okay.
By the way,
So,
Eric, like, feel free to like take all the time you need. It's just, I think I
oh,
really enjoyed it. It's like super great
oh, thanks.
to learn all these details. Also, that we like go a little bit further into what's like behind it than you originally planned. So yeah.
Oh, great. Thanks for that. Okay. So, so far we had talked about all of the layouts that we've mentioned so far sort of like intuitively cover all of the space that they could. In other words, I'm not sure that really makes any sense, but so this one that we looked at here, 224:124, all of the integers between 0 and 12, not including 12, appeared, right? So here was 1, 2, 3, 4, here was 4, 5, 6, 7, here was 8, 9, 10, 11. But that doesn't need to be the case. So we could have a very simple non-contiguous layout would be something like 3, column, and 2. Okay, so that is just what you're going to get there is, if I kind of draw out, here is the I direction. That's I. This is kind of silly because there's only one direction, but okay, it's just going to be 0 to 4. So that is going to take in I values, I equals 0, I equals 1, and I equals 2. Those are the 3 allowable values, and output the offsets. Maybe this is clear, maybe it's not. So this one would map to offset 0, this one would map to offset 2, and this one would map to offset 4. So that there are these kind of like gaps here, and that's totally fine.
So, but I would say that that actually, strictly speaking, like, we already had non-contiguous with the
maybe so.
subtiles, basically. But they had like still stride 1 and in some for some element, but I
right. No, you're right. Actually, this one was not contiguous because from here to here was not.
Yeah.
Right. That was not just one. Yeah, you're right. Thank you for pointing that out.
But now it's like we have like no longer stride 1 element, and yeah. Okay.
Yes. Yes. So and the way that I'm drawing this, so I want to point out something that is that a flattened stride, I don't really have a way of representing in the picture the difference between like this one. I'm just picking one kind of at random. So this one and its like flattened version, which is like 3, 4, 2, 1, 3, 40. So my picture would not distinguish between these two, but they are, logically different in the program, obviously. So I'm just pointing that out, that flat ones don't look any different in my way of drawing it. So let's take a step forward. So I just want to kind of recap what we said real quick before I move on, because it'll be useful. And that's that, okay, we have this method of taking shapes and strides. Excuse me. The way that you go, so a shape is the allowable coordinates that can be provided to the layout. So this one has I values between 0 and 3, not inclusive, and j values between 0 and 4, not inclusive. That's the shape. The stride tells you how to go from a coordinate to an offset. So the stride goes from I, j to the offset, which is just an integer. And the way that you do it is you dot with the stride. Okay, just to recap, this is what we said before. So, and then we also noticed that the subtile has the same layout. I'm sorry, it has the same stride as the original tensor, but a different shape, a smaller shape. Okay, and a different base offset. So this is kind of summing up what we said so far. And then we saw that these tensors don't need to be contiguous in the things that they output. For instance, this one skipped 1 and 3.
By the way, Eric, is it in like during the implementation? Is there some form of if you take like a sub view of a tensor in CUTLASS, is there then some form of reference counting happening, or is it how is this done in the library? That
so
it's like
yeah,
it's
so there
C
are
basically. So you have to take care that the parent object is still in.
That's a good question. Yeah. So like a lot of C++ libraries, like it just is pretty much infinitely configurable. So this thing that you're referring to is part of the engine. So there is like owning engine, non-owning engine. Does that sort of answer your question?
Yeah. Super great. Okay, it's like everything.
Yeah. Yeah. Anything you want. Yeah, it's like crazy, so just tons of knobs. Okay. So we were looking at this before, but I want to sort of make it more concrete. So let's say we have a big tensor and it's of size a by b by c, and I want to tile it by a smaller tensor that's of size little a by little b by little c. So I should end up sort of logically with a tensor with 2 parts in the output. There should be an outer part which answers the question, which tile are we looking at? And that should be of size a over a times b over b times c over c. Hopefully that makes sense. And then there's an inner part that answers the question, which element in the tile are we looking at? Right? And then assume for now that they all, all the A's divide the A's and B's and so forth. Okay, so that's what tiling should sort of look like intuitively. And I want to think of this as sort of like a division operation on tensors, so that like I'm going to take big tensor T1, smaller tensor T2, and sort of tile it and get like this new tensor T3, which is like T1 tiled by T2. This should make some sense because it's sort of what we were talking about before. I don't know why this keeps jumping around. Sorry about that. Okay. And so generalizing that, we could also just tile in certain modes, right? So in this example I'm talking about, so suppose that I really only care about tiling in modes A and the A and the C modes. So I could sort of think about it as like the outer part has A over A, B, C over C, as like answering the question, which tile are we talking about? And then the inner part is just like the coordinates A and C. And you could sort of insert that like there's an extra like unnecessary 1 in there if you want. So you could say it's of size A by 1 by C. Okay. But this is important in CUTLASS. You don't only want to tile data. Oftentimes, when we think about how these accelerators work, we want to tile up compute resources as well. So you might want to like take a tensor core operation that logically requires a certain number of threads to perform, maybe like an entire warp, for instance. And then it also takes a certain amount of data as well. So I need to sort of like take a tiling pattern that maps both onto compute resources and to data. So I really would like to, instead of thinking of tiling tensors, I'd like to even generalize it and say like, oh, okay, I can tile shapes. And so let's adopt this convention that like if I take two shapes, like if I take A, B, C capital, and I do this like this slash with a circle over it, which I'm just using to indicate like something that we hope is similar to division. So there's no like formal nature to this like symbol I've chosen. It's not like anything fancy. I'm just saying like something that is similar to division. And I'm going to tile it by this like little a, little b, little c. I'm going to adopt this convention, which sort of answers the question from before about like nested modes, where the first mode is going to be the inner one, which answers the question, which element in the tile am I looking at? And the second mode is going to be the outer one, which is like, it answers the question, which tile am I looking at? All right, so keeps jumping. So, and then any leftover modes, like modes that were not tiled at all, you could argue that they should go in the inner one or the outer one. I think they should go in the outer one. So, and then the library sort of agrees with me. So we're going to put the leftover ones in the outer part. So if I'm only tiling in modes 1 and 3, the inner part, which is like a subtile, goes on the left, and then the outer part on the right. Okay, so we sort of got to this before, but like, can we actually, instead of just tiling shape divided by shape, could we actually take a whole layout and divide it by a shape? And as you might suspect, the answer is yes. So the question now, though, is like, if I'm going to take capital A, B, C, and I just picked like the sort of standard layout left, like layout left, the generalized column major one, so 1, capital A, B. Suppose I want to tile that by a shape that is little a, little b, little c. Now the question is like, what is the resulting stride of the inner part, and what is the resulting stride of the outer part? So that's the question I'm going to try to answer now. Well, we kind of already saw it. So the inner part is the subtile. So the inner part answers the question like, which element in the subtile am I looking at? And we saw that a subtile actually has the same stride as the tile that it's part of. So the stride in the inner part should be the same as the big one. Now, what about the stride on the outer part? So let's think about this for a second. So if I take a element, go back to the drawing board for just a moment. So suppose I have a big tensor here that is like m comma n with the normal layout left. and then I have a little m n, which represents a shape, and I'm going to try to divide that. So I claim that, as I was kind of alluding to before, we have this mode. So the inner thing, which answers the question, which element in the tile am I looking at?
So as a general note here, we are still in matrix coordinates, so to say. The first coordinate is like the row in which we're in, and the second is the column in this example.
Yeah. Right. Yeah. So down is the positive I direction, and right is the positive J direction. So if we believe what we kind of figured out before, the subtile should have the same layout as the original tile. I mean, as the original tensor, rather. And then the question is, like, this part that is like has that shape, which answers the question, like, which tile am I looking at? What should the stride there be? And that's what I'm going to try to demonstrate to you. So let's ask this question. So suppose I take an element. These are two adjacent tiles, let's say. And suppose I'm looking at the same element in these two tiles. And then I'm going to draw an adjacent tile in the J direction as well. And I'm just going to, this is how we're going to figure out what the stride should be. And I won't belabor the point too much. But suppose that I fix the inner coordinate and I increment the outer coordinate. Let's say that I increment it by, actually I drew it in the wrong way, so this would be incrementing it by 1 in the J direction, or in the I direction, excuse me. So as I increment the outer coordinate by 1 in the I direction, this x here should turn into this x here. So the question is, how much does the offset change as I do that? Well, I would try to poll the audience, but it's difficult because here we are. But
yeah, I think we could actually do. I mean, it's maybe do.
Yeah, sure. Why not?
So we have a first answer from Jonas, which would be m, like maybe a little.
Yeah. So you're saying that the difference in the offset would be m, little m or big M?
I think it's like little m is suggested here.
Yeah, I agree. So that's right. So we are changing it by a little m. And then in this direction, what if I keep the same inner coordinate, but I increment the J by 1? How much do I change it? So if it's not obvious, we can talk through it. So
MSK Progress says n, and Jonas says n times big M, like capital M.
Little n times big M. Yeah, that's what I think too. I like that. So the way that I reached this conclusion is that I saw that, okay, this difference here is that is little n elements in the J direction. And each time I take a step to the right in the J direction, I'm actually incrementing by capital M. So if I take n steps to the right, each of which increments my offset by a capital M, then I will get a total of little n times big M, right? So n steps times capital M step size. And what I mean by step size is that's how much each step increments the offset. Okay, so, and I'll kind of cut to the chase here. So like and in general, if I have like capital M, capital N, capital K, and I'm going to be like, let's say this is like 1 M, M, N. That's like the layout left. And I tile it by a shape, right? I'm going to take a layout and tile it by a shape. Little m, little n, little k. That's going to be, okay, an inner mode, which is like m, n, k. This is all lowercase. Same layout as the big mode. Okay. And then the outer one is capital M over M, capital N over N, capital K over K, and then running out of space here, the stride is going to be, I take this one and I dot it with the size of the small thing. So I get 1 times little m, I get capital M times little n, and then I get, I'm running out of room. So put it over just a little bit. And then I get,
So you mean element-wise multiply, right?
yes, I said dot. I meant element-wise multiplication. Thank you very much. Mn times little k. Okay, so hopefully that makes some sense. Let me pause for questions here.
Yeah, we had one
Tempted to
question
go
from
give a little tour of the code base. Yeah.
Yeah, we had one question a little bit earlier from MSK Proga, who's asked, is there a typo on this slide on the right side? The first nested shape should be ABC in brackets, braces, not capital ABC. Is it right or not? Yeah, yeah.
Oh, it is little ABC. You're right. Thank you. Yes. The first
Okay,
inner
yes,
should
bro.
have the lowercase, not the uppercase.
It's always good if like people in the audience are really taking care of reading it
Yeah.
thoroughly.
Yeah.
There was also another question. Do we need to do manual padding and tiling tensors for alignment purposes? Maybe it's also if you, I don't know, you will go to the code, like how is it like really represented in CUTLASS in C++ later? I don't know if this maybe then become clearer.
Oh, I'm sorry. I didn't understand the question. Padding and tiling?
Yeah, that's I guess it's the question whether we need to do this calculations, this offset calculations manually, or if it's like done by the library somehow.
No, it certainly is not something that you as the programmer have to do. So that's maybe an argument against me covering it. So that I had to make a choice. Like, do I sort of like take some of these computations for granted and sort of teach you the API? But what I tried to do is what I thought I could add more value. Maybe it's partly because I'm a math guy. Is like I just wanted to sort of present the conceptual part of it, and then hopefully the API can sit on top of that when you learn it. But definitely, you don't have to do that computation yourself. But there is something interesting here, which is like if what if you have sort of the last tile? What if like the capital A, let's say, is not perfectly divisible by the little a? Or often in these kind of like problems, the last tile is a little bit smaller because there's like some leftover and it doesn't work perfectly. So one place to look there is this thing called predicated tensor, I believe it's called. So this is the notion of like sort of keeping around a predicate which tells you like, oh, is this element actually valid? So like I think if I understand it correctly, I'm not sure I know all the details, but like a predicated tensor is like a generalization of a tensor, which also comes with this like sort of boundary condition, which is like, oh, maybe this index doesn't actually exist in this particular tensor, if that makes sense.
Yeah, thank you very much.
Okay, let's look through the code a little bit. And I think we're already well over, so feel free to leave or whatever. But I think it's fun to look at the code and get a sense for it. So, it can be a little daunting at first.
I must say, I'm completely flashed a little bit. I didn't know what the presentation was about. What I expected that Eric would like show a lot of code and not really go into this conceptual thing. And it's like for me a little bit mind blowing. And it really now makes me want to take a closer look at CUTLASS and try it out because it's like fascinating how I thought like I would know a lot about tensors and shapes, and I've like done my own tensor classes, written code for PyTorch and so on. And yeah, this goes a little bit further here with this like arithmetic shapes, so to say. And yeah, I like
Yeah.
it. I need to like definitely spend some time with this.
That's great. I mean, I'm really gratified that you said that because like I was kind of worried that everyone was going to be like, wait, why are we belaboring all of this? Like, because basically I just kind of broke the tie by saying like, well, what would I like to talk about? And I like to talk about the conceptual stuff. So let's do a little tour through this code base here. So I have now opened up, I called it CU as an abbreviation for CUTLASS. So here we're at like the very top level. So it's first of all, it's a header only library. So everything that is like, a moving part is in this like include. here.
Great. We had also like this question really in the beginning. It's what can you give like where's the distinction? Where does like Qt end and CUTLASS start? And so
Oh yeah,
what is what?
that's a good question, and I didn't address that yet. So okay. So first of all, Qt is a framework that is introduced with CUTLASS 3.0, which, as I understand it, is like the end of 2022. So my timeline might be somewhat off, but like the Hopper stuff is like very much integrated with the newer framework of Qt. Okay, so everything I was just talking about with shapes and strides and layouts, that's all part of Qt. So I guess that they had this existing library, and so CUTLASS extends backward a while, and you can see even here on this like Visual Studio Code, the include is even split into Qt and CUTLASS. So strictly speaking, CUTLASS is the superset. It's like everything is CUTLASS, but this part called Qt is the part that was introduced in late 2022, and that's where this like layout algebra stuff lives. And the layout algebra goes quite a bit deeper than I've even indicated. So there's this notion of the product, the composition, the functional composition of two layouts. There's various flavors of like division and stuff that now that actually deciding which of those you want to use in your kernel is something that you, the programmer, would need to know. So as you hopefully get deeper into the library with, I hope this talk gets you started, you will have to ask yourself like, oh, okay, so here I want to do this kind of tiling. I need to take like raked product, which is just one of the flavors of the product of two tensors, and that's all like Qt stuff. So a lot of some things are, I guess I could talk about the answer to this question forever, because it's sort of like the entire library is either Qt or CUTLASS, right? So, but it's that this whole idea of the layout algebra, I would say, is like the key novelty of Qt. And for me, I had to sort of decide like which to focus on. So I tried to learn the newer one, which I think they're trying to write everything now in terms of this newer framework. So I guess I'll just cut myself off there, because I could just keep talking about that, but we want to go through the code. Any other questions?
So for me, it's like really that this is a new concept, this layout algebra, where I think it sounds super exciting, where you have to wrap your head around to like really see all the options and what's possible, how to use it.
Yeah, it's fun, and so I guess for me at least, at my sort of intermediate level of knowledge, definitely not an expert yet, is like, what's the point of like all this layout algebra? And the idea is that tiling, you need to take little tiles that represent like compute resources and data, and sort of match them together in a programmatic way. So like you can think that these, like if you've looked into the tensor core operations, and we'll look at them literally in just a second here, those are naturally occur in like a discrete chunk of compute and a discrete chunk of data. And also often like it comes with a particular type. So instead of me just waxing, let's actually look at them. So here we are in this include, which I said this is like the real heart of it. It's a header-only library, and it's all in this thing called include. And then of course the other stuff is docs, examples, blah, 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 tests. Okay, so if I go into CUTLASS here, I have some files here. These are like very fundamental algorithms related to like that everything touches, that are just in the base Qt folder. So a big one is layout, and then a big one is tensor. And you see stride, pointer, these are some familiar terms. Okay, so let's look here. The first place I want to guide your attention is to these two folders called Arch or Arc, I guess, and Atom. So these kind of naturally come in, these are like kind of dual to each other. So I wish I had just a little more space on my screen, but I don't. Okay, so let's look at this Arch folder here. We see that there is kind of each of the two folders, Arch and Atom, have sort of like two subfolders almost they're not actual folders. There's stuff about copy, and there's stuff about MMA. Okay, so MMA is matrix, multiply, accumulate, and copy is obviously copy. And so these are operations that might not always exactly be tensor core operations, but certainly a lot of them are. So you can see it's also divided by compute capability. So if you're not familiar, this like 5.50 is like 5.0, 7.5, 8.0, 9.0. So 8.0, as I recall, is ampere, and 9.0 is Hopper, and I think 7.0 is Volta, maybe, if I'm remembering correctly. But so you have here these like various operations that are partitioned by like which hardware they actually occur on. So let's like pick one. Let's
Do I have
pick,
as a developer to specify this, so for which target platform I want to develop, or is it like
no, you don't have to. So one question is like, what level of control do you want? So if you don't really want that much control at all, you may just be better off using like something like CUTLASS, which will do a lot of the dispatch for you and figure out what hardware you're running on and stuff like that. And then if you want to go just a little bit more control, there are a lot of things here that will sort of have a sensible default, and where it's like, okay, I'm gonna put in like the default MNA. That's not exactly what it's called, but you understand my point. And then it will say like, okay, what hardware am I running on? Let me go dispatch to that one. Does that answer your question?
yes, to some extent. Can you just
Yeah.
maybe like open and so we can see what's inside
Yes.
these? Yeah.
I didn't want to give away the thing too quickly because it's just so fun. Okay, so look, there it is. That's a tensor core operation. That's inline assembly. And this is, okay, let's look at what it's called. SMA, it says here, the comment says MMA, matrix multiply accumulate, 16 by 8 by 4, TN. Okay, so the T means transposed, and the N means not transposed. So kind of silly, but okay. So here is the literal PTX that corresponds to this tensor core operation. And if you're familiar with inline PTX, you can read this. But if you're not, so this F stands for floating point. Those are what's called constraints. So it comes in these, like, the way to read this is it has three parts, an optional fourth part that's not here. So the first part is what's called the template, I believe. Template is kind of an overloaded word. And this is just like the raw text of the instruction. You can see that it's like strings concatenated. Basically, they're just juxtaposed, which means in C you concatenate them. And then there's a colon separating the other two parts. So here's part 2, and then here's part 3. So it's like, it goes like template, output parameters, that's the second part here, and then input parameters, and that's that third part here. And you notice that the output parameters always have like an equal sign. So that's just part of how inline assembly works. They need to have like either an equals or a plus in front of them. Okay, and what is this up here? Well, this controls how much memory this particular tensor core operation needs to use. So here we have it as, let's see, what is it? 16 by 8 by 4. Okay, so F32, TF32, TF32. Let's go up a little bit. Actually, I want to use...
So is this
Okay.
like a very inner detail of the library, which you normally as a developer would not have contact to, or is it that you really would go at this level? I don't know, this struct name,
Yeah,
for example,
that's a
that you
good
have
question.
and use it directly.
If you look at, so like if you look at like the Flash attention library as an example, they definitely have very low level. It has, it's so focused on performance, and I think Flash attention aspires to be, a subroutine of like a lot of different ways of using the attention layers. And so it does actually like use these levers and say like, okay, if you're on Hopper, I want you to go do that and do this specific kind of like tiling. And if you're on Ampere, I want you to do this other thing. And so like it is in contact with these very low level details. So this is in the arch here, and I want to now go swap over to copy traits here. And I sort of lost my place, unfortunately, but oh, that's the wrong one. I'm sorry. I'm in MMA traits. So MMA traits SM80. That's what we were looking at before. Okay. So every operation that we had, actually, I can split the window. That'll be nice. So, okay. So everything that showed up on this left-hand side here is also going to show up on this right-hand side. These are sort of, like I said, these two dual directories here. And so you notice how this one is a templated struct, and it takes as its argument, this is like a template specialization. So it says like, this is what the MMA struct looks like for this argument of the template. And so this one is like SM80, 16 by 8 by 8, F16, 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 TN. So and then that struct that it's talking about is in the other folder. So I'm just trying to give you like some navigation here of what any of this stuff means. And then, so the MMA traits, the one on the right, is a little bit more readable. So you look here in the struct and it says like, okay, using shape MK, there's the shape. So it says like this tensor core operation naturally occurs in like 16 by 8 by 8. So that's like the M, the N, and the K. And then it has this thread ID. Okay, so that's basically talking about how the threads participate in this operation. And then we have like A layout, B layout, C layout, and you can see at the top here what those things are. So the A layout is like 16 by 8. It's this layout. And then it would go on too long for me to explain exactly how the semantics of all this stuff, but you can see how these tensor core operations are encoded here in these layouts. So let me pause for questions.
Yeah, there's one question from Jeremy who asked basically if this is only available for Hopper, or can it also be used for other, because like the architectures look as if older GPUs would also be supported.
Yeah, I think they have less support. This one we're looking at right now is Ampere. So see how there's more stuff for SM90. There's like each so there's always the Hopper is always like the most supported one. So it has like various flavors of copy, SM90, SM90. And then as you go farther back, there's like less support. And I think they're just trying to point their efforts toward the future. But there's definitely they're trying to represent and to kind of, one thing I didn't emphasize so far is like beyond just like sort of taking care of the indexing and the assignment of threads to data and so forth for you. It's also, the point of this is that, it's always good when your configuration is like declarative, right? So it's like a noun in the language. So you should be able to say like, okay, let me experiment with like 5 different layouts for this particular operation. And I'm just going to put them in an array and sort of iterate through them and run the test for each one, as opposed to like, if-defing some code and like doing the loop in different ways. So these different layouts is a way of hopefully making declarative the layout of the threads and the data and how you're going to iterate over them and which one should be contiguous and which one shouldn't, if that makes sense.
I don't know if you can maybe show a simple example or so. So if I see whereas here we have this copy header or this MMA atom and so on. There, this without the architectures. Is this the one which you would normally include, or would you?
Oh yeah, exactly. You said it. So in fact, there's even, I believe, let's see. So arch copy, and then there's even, like, you see there's algorithm copy. So
Okay.
it's a little bit of a lot of details here. So direct copy for any type, right? So universal copy. This one is going to see there's like more specialized and less specialized versions here. There's just a lot here. So yeah, the one you include, let's look at like a simple example here. So if I go to, okay, well, remind me to double back and tell you a little bit, just like a summary of some of these examples, but just to kind of cut to the chase here. So if I look at this example here, which is like tiled copy, you see that actually all it includes is just like Qt tensor. So that takes care of a lot of things. And then it goes through this whole thing. Make coordinate. Here's these underscores, which is like the colon in Python. Yeah, so I could just talk for a long time, but I'll just wait. I'll let myself be prompted for questions because I don't always know what is the most interesting to people or the most confusing.
Maybe a general question about the scope of the library CUTLASS. Is it mostly about like what we saw now, copy and like matrix multiplications, or are there also like other linear algebra, for example, I don't know, inversion of a matrix or something? Is this also supported?
Oh, yeah. So that's a good question. So I think at this level of detail, so if you want to invert an entire matrix, I think you really want to go to CUTLASS for a really,
Okay.
but on the other hand, if you're doing I think so there's also like cusolve, right? I don't know exactly that all those things, but it might be that you're trying to solve a linear system, and so what I'm trying to say in being kind of a roundabout way is like this library as it is would be some of the subroutines that would be involved in things like LU factorization, or um, like solving a linear system, or so if you want the sort of optimized version and you don't need to turn the knobs yourself, you can go over things like cuBLAS and cusolve and stuff like that. But these operate, and to answer your question, Andreas, there is support for things like convolution of vectors. So there's like other linear algebraic things here, but not like inversion of an entire matrix.
So it's basically the toolbox that you can use
Right.
if you are like have enough time and
Yes.
you want to like a
Yeah.
inverse.
If you're a weirdo like me and you're actually interested in turning these knobs yourself, then this is so you see like and it reveals itself in the kind of libraries that use CUTLASS. So it's like libraries that are like experimenting with new architectures that want to like get really low level and see like so that's why like flash attention is written in CUTLASS, and a lot of other really kind of fun things that aspire to be fundamental.
Is there maybe something
in
like
the
a simple quote matrix multiplication sample or something?
What was that?
We could look at an example of a matrix multiplication, just something simple.
Yeah, that's a great idea. Yeah. Okay. So as I go to a matrix multiplication, I want to remind myself to just kind of give you a couple of pointers for these for the examples here, because that's a great place to learn. So when you go to the examples, there's a lot here. I mean, there's like 50, 60 examples. And then there's a separate folder that's called Qt. And then I'm not sure I understand really what this common is. I never used that. Might just be like little subroutines that like helper methods. There's a Qt tutorial, and it proceeds through some like sort of different ways of doing. So this is SGEM, which if you know like sort of the BLOS terminology, the S is like single precision, and then there's the GE, which is like stands for general. So basically that means like the general case. In other words, just like dense matrices, no sparsity, no like special structure to the matrix. And then the MM is matrix multiplication. So you might see like instead of SGEM, you might see like SGEMV. That would be like single precision, general stuff, matrix times vector. So this is just like the kind of BLAS stuff that's been around since like the late 80s, this kind of terminology. And I think it actually started because Fortran only let you use like 4 characters in your function name or something. But okay, so let's look at SGEM1. And there are definitely we're going to encounter methods that I can't describe to you in total detail, but you can see like the general layout. So let's go down to main. Yeah, so we're going to read in some numbers. And then it kind of, you can see where this is going to call a gem function that is still the host function. This trans A trans B is just specifying whether the matrices are transposed or not. LDA is like the leading dimension of the A matrix. So this is like the capital M that we were talking about before. Alpha and beta. So a lot of these kind of routines are even a little bit more general than matrix multiplication. So I think the most general one is like, it's like D gets assigned, alpha times matrix A times matrix B plus beta C. I'm
So
not sure
normally a
exactly of all
factor
the.
and an offset, which we can.
Yeah, so the alpha and the beta are like scalars. And then, and then there are simpler versions where like, oh, the C and the D are actually going to be combined in this one. So we're not going to distinguish between them, but that's like the most general version. yeah, let me let people's questions sort of direct me where to go. So the next thing I would do if I were reading it, I would go up to this gem. Okay, there's not really much here. It calls gem NT or gem TN, depending on whether the matrices are transposed or not. And I would go up a little bit further.
So the
Okay,
data
here's
types
gem.
for these matrices, is it like there's some vector data type? So do they have also tensor data type, which is like more general? Is it this tensor data type which is used here?
Yeah, these are tensors. So where did it make the tensor? It used some of these, not all of them, in fact, use. Okay, so you see this is device vector. That's
Okay.
just like, I guess, the most general thing. Okay, then it
So
becomes a
device
device
vector is
vector, and
still
then
like a linear block of memory without any
yeah,
shapes and like one
right,
shape is only like the size of it. Okay.
exactly. So yeah, so it's going to pass it by calling this probably like a function that's called like data. So sorry to be confusing and scroll over the place. Yeah, data.get. And then you go up here, and I think the tensor is not even created until a little bit farther in. Okay, so here finally we're actually calling a device function. This is make layout. Okay, so where does it become a tensor? Probably in the next one up. So somewhere around here we're going to see make tensor. Yep, there's make tensor. Okay, so here's something worth noting. SMem pointer. So they have these like tags that adhere to the tensor that like instructs the program like, okay, this refers to shared memory. And then another one would be like make gmem pointer. Okay, this is global memory, so that it can like dispatch to the right method. So I'll pause here for a second and see what questions people have. I mean, at some point we have to stop. I'm happy to keep going, but it just at some point the tree just expands into like infinite branches and levels of detail that we could go into.
Yeah, so there's from Culprit Jean. She asked if it would be like a good thing also to have like block sparse or block matrices to calculate with. I guess it is like because we have this subtiling which we can use, right?
Yeah, so that's something I don't know much about yet, is the support for sparsity in CUTLASS. So I have to kind of punt on that.
Yeah, I'm not sure if like it was about said I block sparse. I think it is what like block matrices. I think this is like what. Yeah, I see. Okay, she said it ideally sparse. So sparse probably not. Or we have to look into later. Okay. So Culprit Jean says it was about block sparse matrices. So I think there are like special kernels which people like, for example, from OpenAI who provide them. Super nice to see like this. What somebody mentioned, like it's like nerd sniping.
I just read that. Yeah, so I think I may have nerd sniped myself with this presentation. So yeah, whether it's a nerd snipe or whether it's useful learning that will accrue to your benefit definitely depends on context, I would say. And I think there's definitely it's always wise to do some mixture of depth first and breadth first, right? Like don't just disappear down the tree and never come back until you die.
Yeah. Okay. So Eric, then maybe let's stop at this point. I want to thank you really very much for this great thing. If your goal was to inspire others to look into this library and to get a little bit fascinated about it, so
Great.
awake this desire to like look into it. For me, you completely succeeded. I will definitely take a closer look at this. And it's like for me, it's like as going to a movie where you have like no information before. So I knew it's like a linear algebra library for NVIDIA and so on. Yeah, so really great. So everybody, maybe like give a big shout out, like some smileys, some emojis
Thanks a lot.
for Eric.
Yeah, it's been a
Say
pleasure.
thank you
And folks, like, if you have questions, I probably don't. I mean, maybe there's a 50% chance I know the answer, but just DM me and I'll try to answer your questions, or I'll point you to where you might find it. But it's been a pleasure.
thanks everyone for joining, and see you next week.